Hello everyone. Today our topic is an array class. So we will be exploring the concept of an array class, a critical component in programming that helps in managing collections of data. Arrays are foundational structures that allow us to store, access, and manipulate data efficiently. So, hopefully, by the end of this lecture, you'll understand how to create and use array classes in your programming, um, in your codes or your programming endeavors. So, here, arrays, as you may know, are used to store multiple values in a single variable. Um, However, using them directly sometimes limits flexibility. That's where an array class comes into play. It abstracts away much of the complexity of dealing with raw arrays and offers additional functionality, such as methods to add, remove, or search elements, all while ensuring memory safety and performance. So, um, before we begin, we'll introduce some important concepts that might be new to you, but so so and it's important to take a step back and familiarize ourselves with few key concepts. These are programming tools and techniques that some of you may not have encountered before, but they are essential for understanding how the array class works. So the first concept is the inline function. Essentially, making a function as inline in C++ is a request to the compiler to insert the function's body where the function call is, which can potentially reduce the overhead of function calls in performance critical code. Next, we have return by reference, which allows a function to return a reference to a variable rather than a copy of the variable's value. This can improve performance, particularly when dealing with large objects or arrays. Then finally, we'll be working with bitwise operators, especially the and or. These operators are used to manipulate individual bits in a data structure and are particularly useful in performance optimization and low-level programming tasks. So now let's talk about inline functions. When a function is called in a program, it typically involves several machine level instructions to handle the call. So this overhead can accumulate, especially in programs where functions are called frequently or inside loops, leading to slower execution. Then an inline function addresses this by instructing the compiler to replace the function call with the actual function code directly at the place where the call is made. This effectively removes the function call from the machine code altogether. So by skipping the function call, the program saves time as no additional instructions are required to handle the call itself. This optimization is particularly useful in cases where a function is small and frequently called, such as getters, setters, or utility functions used in loops. However, while an inline function is generally expected to execute faster, we should use this feature wisely. If a function is too large, marking it as inline can increase the size of your code, which might not be beneficial in every scenario. This is something we will explore in more depth later. Now let's address a crucial question. Should we inline every function? So the short answer is no, but if we elaborate, so while inlining can improve in performance by reducing function call overhead, there are situations where it can actually have the opposite effect. If, for example, we call a function 20 times throughout our code, our compiler would replace each of those calls with 20 copies of the function's code. This can lead to code bloat, where the size of the code becomes too large, potentially negating the performance benefits of inlining and even causing slower execution due to larger memory footprints. So, when should we inline functions? A good rule of thumb is to consider inlining functions that are small and frequently called, particularly in performance critical sections such as loops. Inline functions in loops can reduce overhead and lead to noticeable speed improvements. Um, However, for larger or less frequently used functions, it's better to rely on normal function to avoid unnecessary duplication of code. Next, we'll discuss returning by reference. So, in most cases, when a function returns a value, um, it returns a copy of the data. But sometimes you may want to return a reference to an actual location in memory rather than a copy of the value stored there. This is where the reference return type comes in. So when a function returns a reference, it allows the function to return the location of a variable. So we can use the variable directly in our code rather than a copy of its value. For example, this is especially useful when dealing with large data structures where copying data would be inefficient. Now, a reference return type is particularly useful when you need to modify the original data. For instance, if a function foo returns a reference to a private integer, we can directly change the value of that private integer from outside the function like this: my object.foo x equal to 5. This example shows that because the function returns a reference, the assignment operations the assignment operation becomes valid. If the function returned by value, we wouldn't be able to use the left side of an assignment. Since a value can't be changed in that way, this helps us to optimize our code and avoid unnecessary copies, especially when working with large objects. Now let's see an example of returning by reference in action. So in this code snippet, we have an array of double values. Here we have double values array, and we have 10.1, 12.6, 33.1, 24.1, 50.0. So we then define a function setValues that returns a reference to the ith element in this array. So here we have this double and setValues, this function. So by returning a reference to the element, we can modify the actual values in the array. So if you notice, in the main function, we first print the values of the array before making any changes. Then we call setValues, setValues1 equal to 20.23 to change the second element of the array to 20.23, and setValues3 equal to 70.8 to change the fourth element. So finally we print the values again, and you'll see that the array reflects the updated values. So what this demonstrates is the power of returning by reference. Instead of modifying a copy of the data, we are modifying the original data directly, leading to both efficiency and flexibility in how we manage data in our program. Now let's talk about bitwise AND operation, which is used frequently in systems programming and performance optimization. The AND operator compares the individual bits of two numbers for each pair of bits. it returns 1 if both bits are 1 and 0 otherwise. So here is the in this diagram, you will have we have two binary numbers, A and B. So first one is A, the second one is B, and then the result of doing, if we do A and B, then that will be, the result will be stored on C. So when we perform the operation C equal to A and B, it compares each bit of A and B. Wherever both bits are 1, it keeps the 1. Otherwise, it results in 0. As you can see from the arrows, the result is 101000. This operation is useful when we want to mask or extract specific bits from a number, such as checking certain flag settings in system operations or working with memory addresses. Now let's move on to the bitwise OR operation, which is symbolized by this one, A or B, like a straight line. This operation compares two binary numbers bit by bit. So just like the AND operator, but unlike AND, the OR operator returns 1 if at least one of the bits is 1, and it returns 0 only when both bits are 0. So in this diagram, we have two binary numbers A and B. When we perform the operation C equal to A or B, we compare the bits of A and B. So in positions where either or both bits are 1, the result is 1. Where both bits are 0, the result is 0. The final result of this operation is 111. So the final result is 111110. So 5 ones, then 0. The bitwise OR operation is frequently used for setting specific bits in a number, such as setting flags or combining multiple binary values in system level programming. Now let's look at a basic array class template. This code shows that the outline of a class template that is used to implement an adjustable array. Here are a few important points to note. The file is called array.h, and it defines the class template for an adjustable array. During debugging, we use a preprocessor directive define debug array. This helps to activate debugging related functionalities, which are useful for identifying and fixing issues. Once debugging is completed, we should comment out or remove the defined debug error line for better performance during regular execution. Removing the debugging code helps the program run more efficiently by stripping out unnecessary checks. Then the constructor and the change size function in this class can throw exceptions, particularly if the system runs out of heap memory. This is an important detail to keep in mind when resizing the array dynamically, as it requires additional memory allocation. Then finally, the template includes the include string directive, which allows the array to handle string data types and using namespace standard, which simplifies the syntax for using the standard library. So this array class template lays the groundwork for creating arrays that can dynamically grow or shrink, while also providing mechanism for debugging and error handling. Now here we start with the template declaration at line 10. So this is the continuation of the previous slide, the previous code. So we have template class data types. This line defines the array as a template class, meaning it can work with any data type that we specify when we instantiate it. Then constructor array integer size. Um, this constructor initializes the array with a given size. It ensures that when you create an array object, the memory is allocated based on the specified size. Then we have overloaded subscript operator. At line 15, if you look, we see the operator function. This allows us to access elements of the array using the familiar square bracket notation array index. Importantly, the return type is data type, and meaning it returns a reference to the element at the specified index, allowing us to both access and modify the element. Then we have change size. This function allows us to change the size of the array dynamically. The comment clarifies that if the new size is smaller than the current size, only the elements from index 0 to new size -1 will remain unchanged, meaning no data will be lost in that range. Then we have the length. The length function returns the current capacity of the array. It's marked as inline if you see on line 19, which, as we discussed earlier, allows the compiler to substitute this function's code at the point of the call, optimizing performance. Then we have error handling. The error function returns a string with an error message. This is useful for handling situations where operations on the array might fail, such as invalid index access or memory allocation issues. Now let's take a look at the private members of our ArrayClass template. These are the internal components that ensure the class operates correctly but are not directly accessible from outside the class. First, we have data type elements. This is a pointer to the dynamic array where the actual elements are stored. Since the array size can change dynamically, we use a pointer to manage the memory allocation. Then we have integer capacity, which stores the current capacity of the array. It keeps track of how much space has been allocated for the array, which allows us to handle resizing operations efficiently. Then we have data type DUT. The DUT variable acts as a fallback or dummy return value. If an error occurs, for instance, if an invalid index is accessed through the operator, this dummy value is returned instead of crashing the program. It provides a safeguard for index error. Then we have integer error code. This holds error codes that indicate issues like array misuse or out of bounds array. It's a simple error handling mechanism to provide feedback if something goes wrong when using the array. For example, it might indicate whether an index error occurred or if there was an issue with resizing. Lastly, at line 30, we have the include array.cpp, which links to header file to the implementation of the function in the separate source file. This separation between the declaration and implementation is a common practice in C++ to keep code organized and maintainable. Now we have so let's discuss how error codes are handled in our ArrayClass templates. So in the array.cpp file, we define function implementations for the array class, including how the array handles errors during its operations. We use error codes to signal different types of uses that may occur while using the array. Notice that the error codes are represented using powers of 2. This is a common technique in programming to represent error states in a compact and easily manageable way. It also allows us to combine error codes which using the bitwise operations, which can be useful in more complex error handling scenarios. So 0 means no error, 1 is a non-positive size was passed into the constructor, 2 means an invalid index was used when trying to access an element, 4 is a non-positive size was passed into the change size function. So the binary representation for 1, 2 and 4 are shown at the bottom here. 1 means 001, 2 means 0010, 4 means 0100. So using powers of 2 makes it easy to handle multiple errors simultaneously by combining them. For example, if both an invalid index and a non-positive size are encountered, let's say, so the error code could be 0011, which is a combination of the error codes for both issues. So we are again working with powers of 2 to define our error codes. So we previously discussed the different error codes. Now here you'll see an example of how error code 2 indicating an invalid index can be recorded in the error code variable using a bitwise OR operation. So the example shows how to record this error. Error code OR equal to 2. So by using the bitwise OR operation, we ensure that the current value of error code is combined with the value of 2. This allows us to track multiple errors in one variable without overwriting previous error codes. So for example, if the current error code is 1, a non-positive size error, and then an invalid index is encountered, applying error code bitwise OR equal to 2 will set error code bitwise 02 will set the new value of error code 23 and then combining both error states. So this use of bitwise operations allow us to track and handle multiple errors efficiently. So using this technique, a single integer error code can be used to record all type of errors that have occurred. Here an error code of 0101 means errors 1 and 4 occurred. If error code 2 occurred, it can be detected with if error code and 2. False if error code is 0101. If error code 2 occurred, it can be detected with if error code and 2. It's true if error code is 0110. Now let's take a closer look at the constructor for our array class template. The constructor's purpose is to initialize the array when an object of this class is created. This indicates that our array will handle a generic data type as defined by the user when creating an instance of the array. So the constructor is defined on line 10. This constructor takes one argument size, which specifies the desired size. So on line 17, the array's capacity is set to the provided size on line 17, and the error code is set to 0 to indicate no error. And on line 21, memory is allocated for the array dynamically using new data type capacity, which creates an array of the specified data type with the size given by the capacity variable. So let's see the implementation of the overloaded subscript operator. First we have the template declaration on line 23. Then we have the subscript operator on line 24, which is declared as the inline, allowing the compiler to optimize performance by inserting the function code directly at the call site. Then the conditional compilation on line 26, we have a ifdef debug error directive. This is an example of conditional compilation. So when debug error is defined, the following block of code, lines 23 to 30, will be included during compilation. This block checks if the provided index is invalid, either less than 0 or greater than or equal to the array's capacity. Then it's returning the element on line 32. The function simply returns the error element at the specified index. Let's now see the change size function, which enables us to resize the array dynamically. As always, the first we'll see from the template 37, line 37, then the change size, then size validation. On line 40, you can see the first thing we do is check if the new size is less than 1, and then if this happens, it indicates an invalid size, so we update the error code to 4 on line 42, signifying a non-positive size error, and then return immediately on line 43. So here it is. Then it just returned the capacity. So let's now take a look at the error function, which is responsible for reporting any errors encountered while using the array. So the first is template declaration, then function definition, and then the error reporting. On line 65, we check if the error code is 0, indicating that no error has occurred. If this is the case, the function returns the message no error. Now this is the continuation of the error function. Then on line 67, we initialize an empty string error message that will accumulate error descriptions as we identify different errors. Then on line 68, we check for a non-positive size error using the bitwise AND operator to see if error code has the bit for one set. If this error exits, then we append a message to error message indicating that a non-positive size was passed into the constructor. From line 69 to 72, the message also explained that the capacity was set to 1 by default as a fallback. Then on line 74, we check for an invalid index error using error code and 2. If this condition is true, we append another message to error message stating that the index was out of range. Now to complete our error function, we have one final error condition to handle. Change size on line 76, and then appending the error message on 78 to 81. Then return the full error message after checking all possible error codes. Then the function returns the accumulated error message on line 84. This completes the error handling for the error class, ensuring that any issues encountered are clearly communicated to the user, helping them understand what went wrong. Now let's analyze the three statements presented here and determine which one is invalid. Now on option A, in this case, set values 1 returns a reference to an element in the array. Since it's returning a reference, assigning a new value like 20.23 to it is perfectly valid. The reference allows us to modify the array's values at index 1. This is a valid statement. So option B, this statement is also valid. Here we are printing the value at index 1 of the array using setValues1. Since setValues1 returns a reference, we can use it to output the value, and cout will display it. So this is also valid. Now move on to C. This is the invalid statement because getValues1 returns a value, not a reference. So we cannot assign a new value to it. When getValues1 is called, it simply returns a copy of the values. A copy of the value stored at index 1, and you cannot modify the original array through this function. Therefore, this statement is invalid. Now let's look at a program that uses the ArrayClass template to help us better understand how to implement and debug it. The file we are working with here is usearray.cpp, and it's designed to demonstrate how the ArrayClass works. We start by including the IOStream library, line 4, to allow for print input and output operations, such as printing results to the console. On line 6, we include the array.h file, which contains the definition of our ArrayClass template. Now on line 5, we define debug array. This is crucial because, as we saw earlier in our template, this preprocessor directive activates debug checks to help identify issues like invalid index access or improper sizing. This directive will enable the debug specific code during compilation, helping us uncover problems as indicated by the annotation. So on line 8, we are writing using namespace standard, and then we have two function prototypes here, get elements and calc average. Now here is the main function. If you see on line 15, we create an array nums of integer with an initial size of 2 by calling the constructor. This initializes an integer array using our ArrayClass template. Then calling get elements on line 17, calculating the average on line 18, and then displaying the average on line 20 and returning 0 at the end. This is the body of the get elements function. This is just getting the elements from the user. You will have a user input, and then it will set into numbers, and then it will just use the while loop and do the necessary codes, and then it sets the capacity to the exact number of elements entered. And then this line is used for debugging purposes to uncover errors in the get elements function. If you see, there's an error because for the for loop, it is designed to iterate through the array, adding each element to sum. However, we have an error here. The loop condition uses I less than equal to avnums.length, but this is incorrect because array indicates in C++ start from 0. So the correct condition should be I less than average nums.length. So there should not be any equal sign with the less than sign. Now here the following output is given using the debug array feature in the main program. It's just returning the main program, And then after debugging, comment out all the debugging lines of code. Don't delete. You may need these lines of code again in the future for maintenance. Now after debugging, so this use array.cpp, a program that's demonstrated the use of the array class, and then here you will just comment out the debug line after debugging. Don't delete, as I said. So here this one is for the better array performance, so that it will not check unnecessary checks to slow the process. And then it is the end of getElements function. You will also comment it out, this line. So these are the lines you will comment it out after debugging. Okay, so now move on to destructors. We already know destructors. I think we already learned destructors from our previous previous lecture, but I'll just go through again. A destructor is a function that is called automatically whenever an object is destroyed. So if an array object is declared within a function, the array object will be destroyed at the end of the function. However, the dynamic array is not freed, causing memory leak unless we write a destructor for the array class. So we will have function prototype for destructor. So we'll just go through. So this is the destructor we can have. So when an object is declared locally within a function and the end of the function is reached, and also when an object is declared within a block of code under a loop or etc., and execution leaves the block of the code, we can then we use destructors on that time. And at the end of program execution, the destructors for any remaining objects are called. So these are the ways how destructors are called. And first we can just call the destructor here. Then here array object is passed by value into function foo. Here array is called an actual parameter, the parameter in the function call, and array2 is called a formal parameter, the parameter in the function handling. Here if you look at this, if let's say this is the address 51030 and we have 25 on this address. Now here when array is passed into function foo, a copy of each data member's value is made. Here when the array function is, the address is 51030 is indicating this location, but then the elements pointer in array2 points to the same array. So the problem we can have, problem 1, changes in the array are reflected back to the caller. So this isn't what we want in pass by value. When foo finishes execution, array2 will be destroyed. Calling the destructor for array2 and freeing the dynamic array is the solution we could have. So here one can safely say that this isn't what we want either, the problem 2. Okay, so all TORs. So we already learned about those constructor, destructor and copy constructors. I think we went over all of these on our last lecture. So we'll just move forward here. So the copy constructor, here the actual parameter passed by reference, y. This is the class itself. Constant is for not to change this value. Passing it by value into the copy constructor would cause another call to the copy constructor. A copy constructor is a special class function. Constructor is just a caller function, which is called when an object of the class is passed by value, cause the actual copying code deep copy. So we already had this conversation on our last lecture, so we'll just go through this shortly. I mean, not very descriptive. This is the code example for deep copy. Now in the private, we have integer capacity, integer error code, data type, elements. Okay, so now let's break down when the constructor, destructor, copy constructor, and assignment operator are called in different scenarios. Here on line 1, array integer a 10, this line creates an array object a array object a with a size of 10. Since we are constructing a new object, the constructor is called here. So the answer is B here. So on the second line 2, here we are copying the contents of A into a new object B. This invokes the copy constructor because a new object is being created by copying an existing object. So the answer is C here, copy constructor. Then on third line, we create a pointer ptr that dynamically allocates an array object with size 20. In this case, the constructor is called to initialize a new object, but no copy constructor is involved since it's dynamically allocated. So the answer is B, constructor is called. Then on line 4, delete ptr. This deletes the dynamically allocated object pointed to by ptr. When delete is called, the destructor is invoked to clean up the memory allocated for the object. So the answer is answer is A, destructor. So on line 5, that's the assignment operator. Here we are assigning the contents of B to A. This is not a copy constructor call because the object A is already exists. Instead, this invokes the assignment operator to copy the contents of B into A. So the answer is assignment operator is called. These examples illustrate when each of these special member functions is called during object lifetime management in C++. Understanding these calls is crucial for managing memory and ensuring proper object copying and destruction. Now here we are looking at how the deep copy operation is related to the overloaded assignment operator in the array class. Now this code shows the implementation of the overloaded assignment operator. It takes a constant reference to another array object on the right as input and assigns it to the current object. In C++, if we don't define our own assignment operator, the compiler provides a default one. However, the default only performs a shallow copy, which means that the new object simply points to the same memory location as the original object. This can lead to issues, particularly with dynamically allocated memory like in our array class. To avoid shallow copying issues, we need to implement a deep copy. The first step here is to deallocate the memory currently used by the object. This ensures we won't have any memory leaks when we reassign values. After that, we call deep copy function in line 5, which duplicates the data from the right object into the current object, allocating new memory and copying the contents of the array elements by element. This ensures that each object has its own copy of the data, avoiding shared references to the same memory. Now then returning this at the end, line 6, we return this which allows us to chain assignment operations, returning a reference to the current object allow us to write statements like A equal to B equal to C. Okay, so Here in this slide, now let's walk through the implementation of this box class, which is designed to represent a 3D box and compute its volume. First, the constructor box. Initialize the box with default values of 2.0 for length, breadth, and height. If no values are passed, the box will default to these dimensions. We also have a cout statement here in the constructor that prints constructor called whenever a new box object is created. Then volume calculation, which calculates the volume of the box using the formula length into breadth to height. This function is straightforward and returns the calculated volume. Then comparing boxes, the compare box and box function, line 15, compares the current box with another box passed as an argument. It uses the volume function of both boxes and compares them. The key syntax here is start this dot volume, which dereferences this pointer to access the current object's volume function. It then compares the result with the volume of the box object passed as a parameter. The class has three private members, length, breadth, and height. These hold the dimensions of the box and are only accessible within the class's function, ensuring encapsulation. So this example shows how a simple class can be designed to handle object initialization, compute values, and compare objects using object-oriented programming principle. So this is all for our today's lecture. Let me know if you have any question or concerns. Thank you.